All right, our next talk will be towards making homomorphic encryption easier to use, given by Alex Malozemoff from Gawa.
Thanks for the introduction. So I'll be talking about some work we did joint with New Jersey Institute of Technology about a year ago, and we will be extending it shortly. This was part of a seedling for IARPA, and we'll be continuing work on it in an upcoming IARPA program. So as we all know, homomorphic encryption is great. People claim it's the holy grail of cryptography. It does all these good things. And indeed, there's a strong push in industry towards using homomorphic encryption more. So Microsoft has their SEAL library, which they've been pushing a lot. Intel has been doing some work on applying homomorphic encryption to machine learning. And there's even startups in the space, such as Duality Technologies, that are trying to sell homomorphic encryption solutions. So there's a lot of interest in this space. However, HE does have some drawbacks. The first is that it's pretty complicated to use. You kind of need to be a crypto expert to understand the different trade-offs and choices you'd make when building a system that uses HE. And secondly, there's still, of course, as with all of secure computation, there's the general concern about performance, although this is under active research and improvement. In this talk, I will focus solely on the usability aspect of HE and ignore the performance concerns. So if we look at kind of the Venn diagram of what you would need to build a domain-specific solution in this space, say you want to use homomorphic encryption for machine learning, right now you kind of need to be a crypto expert, a machine learning expert, and a programming expert. And while there's a bunch of people in the space of machine learning and programming, it kind of gets smaller and smaller, and there's really very few people that kind of intersect all three. And so we wanted some system where we can kind of ignore the crypto side as much as possible, or kind of hide it under the covers. As further example, here's a very simple function in HE library that we use in our system called Palisade that adds three numbers together. Not picking on Palisade here, it's just these libraries are built in C++. Homomorphic encryption is complicated. And it's tough to expect someone who maybe works in higher level languages and is not an expert in crypto to build, to implement such a thing. Yeah, so as I mentioned, most people writing, say, machine learning algorithms or analytic software expect to use languages they're familiar with, like MATLAB, R, Python as well, and another language in the space, which is more recent, is Julia. And so what we really want to do is build systems that allow these people to use homomorphic encryption, use secure computation more generally, without being experts in that area. So in this project, we built a library in Julia that's kind of like a first step in this direction. So it allows function evaluation of Julia functions to be run in using homomorphic encryption. So it has a relatively simple API, standard public key operations for key generation, encryption, and decryption. And the big one is the evaluate function, which does the homomorphic evaluation. Everything is wrapped here within this FHE package in Julia. And this code kind of reproduces that C++ code that I showed earlier. So you can encrypt these three values. You can evaluate those ciphertexts using the sum function, and you can decrypt the result and print the result. And one particular thing to note, which I'll get into a lot later, is we're directly evaluating the Julia functions. So we're just taking the default sum function in Julia and applying it. So why do we choose Julia rather than some other language? Well, we wanted to target a standard numerical computing environment that these people would be used to, such as MATLAB, R, Julia, or Python. We chose Julia for a very specific reason. It has very powerful introspection capabilities that allow you to modify the abstract syntax tree of the underlying code and even the LLVM compiled code. And this allows us to do rewriting of the AST, which makes a lot of these things easier to do. So in particular, we can extend the language and modify the compiled code without needing to modify the compiler. There we go. As a plus, it's open source and under active development. And so there's a growing community in this space, which makes it a lot easier to work in than maybe something like MATLAB. Okay, so how does this system work? So suppose we have this case. Yep. So we are only doing arithmetic operations. We kind of punt on Boolean. Yeah, we're not doing mix. The tool would fail on examples that it doesn't. So in this, so I'll just run through a example here. So suppose we have some user here that wants to encrypt its DNA and run some functions on it. The context here, CTX, contains all of the crypto-specific parameters as well as the networking information. So this maintains the public-private key pair and whatever else you would need to run the encryption and evaluation. When evaluating, the way this works is we take the Julia function, say fn written in standard Julia, and we compile that to an arithmetic circuit, and then feed that arithmetic circuit as well as the encrypted input to our underlying HE library, which is Palisade. And that computes over the arithmetic circuit on the encrypted input, gets some encrypted output as a result, sends it back, and we can decrypt that. So brief interlude on Palisades. So as I mentioned, this is in collaboration with NGIT. They've been developing this Palisade library. It's really a generic lattice crypto library, but it has a lot of capabilities for homomorphic encryption and implements a bunch of different HE protocols. That you don't, but you can locally use. Yeah. Well, it's I guess it's not a very compelling example if you're just running it locally, because then why use HE? The main benefit would be for outsourcing some computation. I mean, there could be settings where, where you wouldn't trust, I guess, your machine or whatnot. But generally, right, if this user had the DNA and the function you wanted to compute, but you can absolutely run this. Most of the examples that we did, it was running locally, just because it's easier to play with. So Palisade is a general lattice crypto library. It also implements HE schemes as well as proxy encryption and other lattice-based things. So So what is the main challenge with this approach? It's really going from this imperative language, Julia, where there's state that can be modified, and in particular, it's kind of a semi-dynamic language. And we want to convert that to some representation, an arithmetic circuit that has no control flow, no memory, and very limited operations. And the way we do that is we use symbolic execution. So this is a technique, I guess, from the PL community. Basically, the idea is you can, instead of evaluating on concrete inputs, you can evaluate a function on symbolic inputs. You treat them symbolically. And then explore run the computation, explore all the execution paths of the program, and as an output, you'd get a symbolic expression. And given that symbolic expression, you can then do a direct translation of that symbolic expression to a arithmetic circuit. So as an example, for this simple case here, using symbolic execution, you get back some arithmetic circuit like this. And that's the main technique we use for translating the imperative Julia code to this circuit representation. So as an example, so this is a simple function written in Julia that does some simple image sharpening. And it has a weight matrix that it goes through the image and multiplies it in, returns some result. And this is how you could write the function in Julia. There's the reason the asterisk is there is because we kind of wrote it knowing that it would work within our system. But it is a Julia function, and it is, there's nothing here that's specific to AG. And to run it, you can basically run it using this the Julia library directly. And again, there's nothing here that specifies that you're using AG. It only comes in when you run it. And I'll walk through each of these steps and why they are the way they are now. So, yep.
Thanks. So what about operations like small, large, rounding, things which are not algebraic? I mean, can you express these things too?
So currently, no.
Well, that's in some sense the core of the power of FHE and stuff like that. Is those things. Maybe it's only in the crypto system, maybe not in the application.
Yeah. So like, what examples? Like, so right now we're using
like bit decomposition.
Yeah. So this is working over the arithmetic focused, I guess, HE schemes. There's other ones like TFHE that work over Boolean, and there's ones that work over fixed point. We are specifically using, I think, BFV as our scheme, which works over arithmetic circuits. Yeah, so by producing a arithmetic circuit, we can compute the multiplicative depth of that circuit and do parameter estimation based on that. It's a somewhat naive parameter estimation, and it is, I guess, overly conservative. So it's yes.
Another question back here. Your code has loops in it. I'm just wondering how that plays out with this symbolic evaluation technique.
Yeah, and I'll get to that later.
Okay.
It works, but is slow. Yep. I haven't looked into that. I remember, yeah, I think in also the snarks for C work, they also use symbolic execution to convert from program to a circuit. It's the same type of approach. So yeah, so For key generation, because as Muthu said, we're not here using full FHE, we're really using leveled HE. And so we need to choose the key public key, the key parameters appropriate for the function we want to compute. For keygen, we can take as input the function and the potential size or max size of the input that we want to run that function on. We convert this function at the low level Julia AST level to an S expression, which we then feed into a symbolic execution tool we built at Galois, which is not just for this project, but is useful just as a general symbolic execution engine called Crucible. As output of that, we get an arithmetic circuit. And using that arithmetic circuit, we can do some naive parameter estimation to choose keys that are appropriate for the specific function and input size we're considering. Encryption is pretty straightforward. For evaluation, we can do the same thing as keygen, except here we're feeding, there should be an error here, but we're feeding the actual ciphertext into Palisade to actually do the computation. And encryption is as you would expect. One nice feature we get by using symbolic execution is we essentially get program equivalence kind of for free, because we're getting as output these arithmetic circuits. There's tools, there's existing tools for doing circuit equivalence checks, and so we can apply those tools in the setting. So in this example, we have two implementations of determinant, this kind of naive implementation on the left, and the more complicated one on the right, and we can, for fixed input sizes, prove equivalence of these functions. So this is kind of a nice bonus feature. Another nice feature that we get out of using Julia and the ability to rewrite the AST is we can do inline HE. So consider this linear regression example, and suppose you want to outsource or run specific portions of this function within homomorphic encryption. So in particular, you want to do this over encrypted X and Y and say run these specific operations using HE. You only need to do a small modification to the code to get it to work in the setting. So obviously you need to encrypt those inputs, but then we can directly, using Julia's macro support, kind of inline these operations. And this will run this computation, decrypt the results, and return it. So it makes it easier to kind of do line by line HE evaluations. The network, so in this example, the context which I talked about recently is implicit. It's kind of this global context that if it's not specifically specified, it will be used, and that context can retain the client or the networking information. So if you kind of do that under the hood. But yeah, in this example, it's being done locally. So just to summarize what we've done thus far, we have a Julia library for running functions using HE, and the key way we do that is symbolic execution. One thing to note, this is a limited prototype. It works for those examples I showed, but we haven't made sure it works for all of Julia, and so it's still a beginning prototype. In terms of where we want to go from here, so I've been kind of talking about how great symbolic execution is, but as the question kind of hinted at, it has some serious downsides. One thing is efficiency. So loops need to be fully enrolled. You're doing this symbolic evaluation, so if you're looping, you need to unroll loops fully. We're creating circuits from this. This can create massive circuits. It doesn't scale well as the complexity of the function grows. The other thing is it's not the nicest user experience in the sense that you don't really get feedback on how long it's going to take to run or if it's going to get stuck or whatnot. So in the future, we'd like to move more towards what you can call a normal compiler with maybe symbolic execution on the side to help. You can think of only doing symbolic execution on the body of loops rather than the loop itself. We've been doing some initial work in the space with some people at MSR, trying to design a intermediate representation for homomorphic encryption that's kind of more like an assembly language rather than a circuit, but that's still work in progress. Symbolic execution is nice in some other ways, like doing program equivalence. Some people we talked to about this work seem pretty excited about the program equivalence. So it seems something that could be useful either in this tool or separately. And then, of course, extending beyond HE. So right now we support just arithmetic computations, but there's plenty of other computations and also security paradigms that you'd want to consider. And it would be nice to extend this approach to those as well as specific optimizations that are catered to the paradigm. So that's everything on the Julia AG library. I'll just briefly mention some other work that we're doing at Galois. So we've been doing a lot of implementation of building MPC libraries in Rust that we're going to be making open source over time. We're really focusing on something that can be maintained, hopefully easy to use, relatively efficient, although the goal is really more the other ones rather than efficiency. We want to be kind of within an order of magnitude, but we're not trying to be necessarily the most efficient, although if we can get there, that would be nice. And because we're using Rust separately at Galois, we've been looking into formal verification of Rust code. So ideally, we'll push in a direction where we can formally verify these implementations. So as I mentioned, we'll be making these open source. A couple of them are open source already. So we have this MPC utilities library and a OT library as well as a garbling library for Boolean and arithmetic garbling approaches. They're still, you can say they're still research prototypes. We haven't hit version 1.0 yet. So if you're interested in playing with them and providing feedback from either the API or code itself, that would be great. And we should have oblivious RAM and garbled circuit-based two-target computation, semi-honest, covert, and malicious, coming up shortly. And I think that's it. Here's some contact info if you're interested, and also we're hiring, so if you want to talk to me about that, let me know.
So you mentioned briefly that you were thinking about ways of reducing circuit size. So when you talked about the efficiency problems, my first thought is that maybe one approach would be to think about how to parallelize the evaluation of the circuit, because that seems easier. So do you have any ideas on, isn't like the size of the circuit kind of intrinsic to? Well, so really, so sorry, let me just finish. I didn't make the question right. So is this really a problem of how you generate the circuit? Or is it like something intrinsic in the model of computation?
So ideally, we would like to avoid generating the circuit in the first place. So by streaming the circuit or doing something like that. So for example, for loops, right? We can design some, say, like some HE assembly language where loops are retained. And as long as we're looping over public values, you don't need to convert that to a circuit. And so there's things like that you can do to avoid this circuit blowup. If you're looping over a private value or branching over a private value, then it's like trickier, and yeah, that that blow up is inherent, but I think there's a lot of examples where you can avoid that blow up. The memory and, I mean, the performance of running symbolic execution on complicated functions, it blows up really fast. And these circuits become huge. And so there is a memory concern of now you need to have this massive memory, or sorry, this massive circuit, even if it's on disk, it could get gigabytes.
Like you have estimated the memory requirement, like you've seen your performance.
So we've generated circuits that are in the gigabytes. And I think right now, the way we're loading it in is we're just loading it in. So you can obviously be smarter about how you're reading from the circuit. In our prototype, I think we just loaded it in the memory. But I would say it's less so memory because you can always store the circuit on disk and then stream it. But it's more the compilation time and the disk space needed to be able to store this.
Thanks.
Is there a way to do this in a kind of lazy way or in a way that's more hierarchical? So it's not a single gigantic thing and you actually build it somehow on the fly?
Yes, and that's what we want to move towards. So really what we would, I think, ideally want is the ability to compile to some homomorphic encryption IR that is much smaller than unrolling the full circuit. But maybe there's some sections of that if you're branching on a private value or whatnot that you need to fully enroll, and then only those sections you would. I don't know if that answered your question or not. We can talk later.
Yeah, so I just wanted to ask, so is the blow up coming from the fact that you're doing symbolic execution? I mean, at least when it comes to private values, this has to be inherent, right? As the other question.
So, yeah, when it comes to private values, it's inherent, but like in this example, well, go back here. In this example here, these loops are over a public value, the size of the
I see.
image.
So you're unrolling even
And
the
we have
public
to
stuff,
unroll
and that's
all
why
of
you're
that,
getting blow
yeah.
up. Okay, all right. So really, what you want is a mix of circuits with normal code. That's what you're calling the
exactly.
assembly for HE.
Yeah.
Yeah. Okay.
So no, not currently. That's in terms of performance, that's priority number one because that's where you get reasonable performance in HE. We just haven't done that yet.